All right, so yesterday we talked about work energy theorem, okay, and we said that work energy theorem is that work is a change in energy. Okay, if you're going to change the potential energy or the kinetic energy or both of an object, then you must do work. Okay, doing work consists of exerting a force over a distance. Okay, that's what work looks like. Okay. And then at the end of the day yesterday, we talked about gravitational potential energy. Okay. So your gravitational potential energy, your ability to do work, okay, or potential to do work due to your position, is related to the mass of the object, the gravitational acceleration. On Earth, that's 9.81 meters per second squared, and the position or height of the object. Okay, those three things affect your gravitational potential energy. Everybody all right with that? Then, let's look at the next kind of energy. Okay, so kinetic energy. Kinetic energy is the energy that actually does work. Potential energy doesn't do work. It can turn into kinetic energy and then do work. And that's why it's only potential. Kinetic energy is the energy you have because you are in motion. Okay, so you are moving. Two things can affect your kinetic energy. Okay, those two things are the ATA is calling me because they don't think I'm busy right now. Okay. So this is the formula that calculates kinetic energy. Okay, so kinetic energy is related to two things: the mass of the object and the speed at which it's moving squared. Right? We briefly talked about this yesterday when I was telling you about Barry Bonds and his corked bat. Okay? And I said he corked his bat to make it lighter. Okay? Because he understood that he could swing a lighter bat faster. Now, I don't know whether Barry understood this part of it, but speed is the bigger part of kinetic energy. Okay? So the faster you can swing the bat means the farther you can hit the baseball. Right? It has more of an effect than mass does. Okay? So it would be better to have a lighter bat. Right? It's why basically every bat in the major leagues is identical. Okay? They're a Louisville Slugger and they're a big hunk of tree that has exactly the same mass. There are regulations around how big a bat can be. Okay? It's also why you never see an aluminum bat in the major leagues. Okay? They're lighter. Right? You can swing them faster, so they don't want that. So kinetic energy is related to your mass and your speed. Okay, so tell me this. Which is more terrifying? A child on a tricycle moving towards you at 5 meters per second, or a bus moving towards you at 5 meters per second? The bus. Now you can reach out and stop the kid on the tricycle. Don't try that with the bus. Just get out of the way. Okay, because you are not stopping the bus. Even if it's only moving at 5 meters per second, it's got a lot of kinetic energy thanks to its very large mass. Okay? Now I'm going to ask you a question differently. Okay, so I'm going to ask you this question differently. Now, same kid on the tricycle, but now they're moving at 300 meters per second. I don't know how. Okay, we won't ask how the kid on the tricycle is moving at 300 meters per second, but that's like almost supersonic. Okay, like they're about to break the sound barrier and be followed by a sonic boom. Okay, and the bus is still moving at 5 meters per second. Now, which one's scarier? The kid? Yeah, he's moving really fast. Okay, fast enough to do a lot of damage, even though he has a small mass. Okay, this is the principle behind a lot of like ancient weaponry, but also modern weaponry. Okay, how heavy is a bullet? Not very heavy, right? They have a very small mass. but they're quite deadly because they move very fast. Like if I just pick up a bullet and throw it at you, not that I would ever do that, but you're not going to get hurt by that. Okay? It doesn't have enough kinetic energy. Okay? And it has very little mass and it's not moving very fast. Okay? But if we're looking at a bullet that's been fired, okay, that's got a lot of kinetic energy because it could be moving at like anywhere, it depends what it was fired out of, but anywhere between 300 and like 1,000 meters per second. Okay, or sometimes even faster than that, depending on how it's fired. Okay, so something very small can still do a lot of damage if it's moving very, very fast. Okay, and so I say this in the kind of context of weaponry. How many people have heard of a railgun? Okay, a railgun has been up until recently kind of science fiction. Okay, but they're actually working on it and have developed working models, but they're huge. Okay, so a railgun works like this. You have a projectile. It's not overly large. Okay, it's basically just like a shell. Okay, so basically just a bullet. But instead of being fired by an explosion, as most shells and bullets are, it is fired by using magnets. Okay, so there's a bunch of magnets in a row, and those magnets push on this shell, and they can make it move at incredible speeds. Okay, faster than any bullet could ever be fired by a chemical explosion. All right, these shells don't even have to be explosive to do damage. Okay, when you see naval vessels firing shells at each other or artillery, they lob explosive shells. And when they hit the ground, they blow up. Okay, that's how they cause their damage. A railgun just shoots a big hunk of depleted uranium. Okay, so just a big hunk of metal. Okay, that's, you know, it's heavy, but it's not super heavy. But it moves so fast that it can just rip through the armor of a tank or a boat, okay, like a naval vessel or something like that. It doesn't even have to explode. It's just got so much kinetic energy that it can just rip a hole through it. Okay, so the benefit of that is you don't have to carry with you any explosive ordnance. Okay, what usually sinks ships is their own weapons blowing up when they get hit. Okay, it's not so much that somebody hits them enough times that they sink, it's that they hit their own weapons and their weapons blow up. Right? So if you were a vessel that didn't have any explosive ordnance, you wouldn't have that problem. Okay? You would just keep firing these depleted uranium shells at really high velocities and poke holes in your adversaries. Okay? The other advantage of shooting something really fast is you don't have to lob it as much. Okay? Most shells have to be lobbed at a high angle and have them come down. Okay? There's a lot of things that can affect how they move. If you're firing with a railgun, it goes so fast that it hardly drops at all. Okay, so you don't have to lob it. You can basically aim straight at your target and hit it. All right, so kinetic energy is affected by those two things. We're going to go over a work energy kind of real world example here in a minute. But first I'm going to show you some fun videos of people breaking stuff. Okay, so the whole principle behind being able to break boards and bricks and things like that with your hands and feet, okay, is that you make your hands and feet move really fast. Okay? Now, you or I can't just walk up to a bunch of boards and swing our hand at them and think that we're going to break them without consequence. Okay? The people that do this have trained for years to do it. And they build up very dense bones as a result. Okay? Every time you even walk, lift something, hit something, okay, you cause microfractures in your bones. Okay? And then those microfractures heal back and your bone gets stronger and more dense. For someone who breaks boards or bricks on a regular basis, okay, they're always doing that. So their bones are getting broken, you know, microscopically, okay, and then healing back stronger and stronger and stronger. Okay? It's kind of why if you have like a grandparent who has osteoporosis, right, they kind of get hunched over because their bones get really weak. One of the first things they tell people with osteoporosis to do is to walk and lift weights, not like go to the gym and put a big bar on, okay, like those little ones that are almost a joke, okay, that are tiny. Okay? Just little amounts of weight cause microfractures in your bone, make them heal back stronger. Okay? It's actually impact that makes your bones stronger. Okay, so they'll tell them to do that. Now, key to this high velocity. You want to break boards with your hands, your feet, okay? High velocity. Other part of it, don't use the tiny bones, all right? If you are like clenching your fist and you hit something, okay? If you're not doing that on a regular basis, so what are the chances you break your hand? Pretty good, okay? Have you ever noticed that in lots of martial arts, the hands and the feet are not used for striking? But the elbows and the knees and the shins, all the heavier bones that are less likely to break, okay, are used more often. Okay? There's a reason for that. Okay? You can break these bones because they don't have very much mass very easily. Okay? But the heavier bones are less likely to break. All right. Okay, so you kind of get the idea, right? Like speed's an important part. Obviously mass is too, okay? But speed is the bigger part of that. Okay, so any object that's moving has kinetic energy. It's part of an object's total mechanical energy, okay? But it's the one that actually does work. Okay? All right, and we can use kinetic energy of anything as long as it has mass and is moving. Okay? It's how wind power works. Yeah, we often think of air as being very light, okay? But when you get a lot of air moving together, okay, can it do a lot of damage? Right, like in a tornado, that's just air, okay? Air is light, but you get it moving at, 180 kilometers an hour, it can do a lot of work. It has a lot of kinetic energy. Okay? And it's why, down by Lethbridge, Pincher Creek, that area, we can use, there's enough wind down there that we can use it to generate electricity. Okay? The mass of that air moving past those turbines, okay, can turn the generator, okay, and make electricity. Right? So even stuff that's really small, once you get it moving, okay, can do a lot of work.
Can I play that?
Yep. Put your phone in the pocket first. Okay. Everybody all right with that idea? All right, so kinetic energy, like we said, okay, is going to, EK is going to be in joules. All right, now remember that yesterday we talked about how a joule is a kilogram meters squared per second squared. Okay, those are the fundamental units of a joule. All right, so when we use this formula, 1/2 mass times the speed squared, the mass will be in kilograms and speed is in meters per second, but if I square it, it'll be in meters squared per second squared. Okay? So it still works out to a joule. All right, so things to remember. Mass, always in kilograms. Okay, and V actually should be the speed, okay, because energy is scalar. Right? So the speed of the object in meters per second. Okay? Sometimes a question will try and trick you and give it to you in something else, like kilometers per hour or something. Okay? It needs to be in meters per second, or obviously you don't get kilogram meters squared per second squared. You get kilogram kilometers squared per hour squared, which is not a joule. Okay? Do I need that one anymore? All right, let's look at this work energy theorem situation. Okay, what's the speed limit for a playground zone? 30 kilometers per hour. Okay, why? Because there's kids, and kids don't look. It's why the symbol for a playground is a kid chasing a ball. Okay, that's what they'll do. Okay, it doesn't matter, trust me, as a parent, it doesn't matter how many times you tell your kids, look before you cross the road. They're gonna just dart out into the street. Okay, that's the nature of kids. Right? It's why we have special speed zones everywhere. It's why we have special speed zones in construction zones. There are people at work. They can be distracted by the job they're doing and not see a car coming. So we demand that people slow down. Okay? But here's the physics behind that. Okay? If I'm traveling in my car through a school zone or through a playground zone and I need to stop suddenly, I need to take all of my kinetic energy and make it what number? 0. Yeah. because my car is still going to have mass, but I need it to be stopped so that I have no kinetic energy. Well, remember that work is a change in energy. Okay? In this case, I want to change my kinetic energy. I want to make it smaller. I want to make it 0, actually. Okay? So, delta always means change, which means final minus initial. Okay, so what we're looking at on this side of the equation is our final kinetic energy minus our initial kinetic energy. What do I want my final kinetic energy to be?
0.
Okay. So what I'm going to do is I'm just going to take this out. Okay, I'm just going to say it's 0. I'm just going to take it out. All right. Now I'm also going to take out the negative here, right? Because the force on the other side would also be negative. I'm just going to make them cancel each other out. All right. So bring this up. Whoop. On this side here, I have work. The work that has to be done has to equal the kinetic energy my car has the moment I slam on the brakes. Agreed? Because I want to go from that number to 0. So the work that has to be done is however much energy my car currently has the moment I slam on the brakes. I want it all to go away. All right? Now, here's where that work goes. Okay? The brakes do the work, or the car does work on the brakes would be the most accurate way to say that. So when I slam on the brakes, okay, the calipers, okay, push the pad against the rotor, okay, and it creates a ton of friction, right? That friction turns the kinetic energy of my car into thermal energy, heat, okay, sound, and even light. Okay, so my kinetic energy turns into those 3 things, and then I lose it and I slow down. Okay, so here are the numbers we're going to need for this. I want to calculate how far I will travel while stopping from 30 kilometers per hour. Okay, so here's what we'll say is true. My brakes can cause the formation of 12,000 newtons worth of frictional braking force. Okay, that's pretty average. The mass of my vehicle is 2,600 kilograms. Okay. And my speed, because I'm a responsible person, is 8.3, repeating, meters per second. That's 30 kilometers per hour in meters per second. Okay, so what I have is this. I need my brakes to steal the energy, the kinetic energy my car has, so that I stop. So what I'll have is force times distance equals 1/2 the mass of my vehicle times the speed of my vehicle initially squared. Okay, if I've been saying the same thing all the way along, work's a change in energy, force times distance is equal to final minus initial. The final is 0, I took it out, so now I'm down to this. How would I isolate D? Because I'm trying to solve for how far the car would travel in stopping. Yeah, divide both sides by F, right? I just want to isolate D, right? So all I have to do is bring F over here. Okay? Not ridiculously complex algebra. Okay? I moved one thing. All right, so now, can I plug in numbers? Do I know all of these numbers over here? I do. Okay, I know all of these numbers. All right, so I'm going to have 1/2 times the mass of the car, 2,600, okay, times the speed of the car, 8.3, squared, divided by the force the brakes could exert, 12,000 newtons. All right, so 0.5 times 2,600 times 8.3, repeating, squared, okay, and then divide that by 12,000. Okay, so my car is still going to travel 7.5 meters before I stop, even at 30 kilometers an hour. Okay, is that a lot? Well, it's from me to the wall at least. It's a long way if a kid runs up in front of your car in between here and there. Okay, but as soon as I slam on the brakes, do I have less and less energy? Okay, like I would be probably down below a lethal amount of energy pretty quickly, okay, if I'm going 30 kilometers an hour, which is of course the intention, okay? In reality here, I probably picked a bad number for that force. It probably should be bigger than that, okay? Because at 30 kilometers per hour, you can stop in usually less than 3 meters, okay? That's the whole reason we have that. Now, how much further would the car travel if I was going 60 instead of 30? Not that I would do that because that's stupid. But how much further would I travel if I'm going 60 rather than 30? Okay? I mean, our gut says double, right? Right? You're going twice as fast, take you twice as far to stop. Except speed is squared in this formula. Okay? So watch what happens. If I'm going 60 instead, so now I'm going 16.6, repeating, meters per second. Look how far I travel. Same formula, okay? All I'm doing now is I'm substituting, I'm substituting 16.6 in here. All right, so 0.5 times 2,600 times 16.6 squared divided by 12,000 newtons. That a lot further? Watch what happens here. If I divide that by how far I traveled in the first situation, it's not twice as far. 4 times as far. Speed has an exponential relationship with kinetic energy. Okay? So if you double your speed, you don't have twice as much kinetic energy, you have 4 times as much kinetic energy. If you triple your speed, you don't have 3 times as much, you have 9 times as much. And if you quadruple your speed, it's 16 times more. It's exponential, okay, because V is squared, right? It's why they have a 0 tolerance for speeding in playground zones and school zones and construction zones, because the relationship between how fast you're going and how deadly you are is exponential. Okay, 30 meters to stop versus 7.5. Guys, 30 meters is 1/3 of one of the straight sides of the running track. Okay, it's basically the distance from the start line to almost the path that goes across. Okay? Can you imagine if a kid ran out in front of you and you slammed on the brakes and you were going to travel 30 meters before you stopped? Okay? Like, you'd have no hope of not hitting that kid. Okay? It's a big deal. It's why you shouldn't speed ever, but especially in school zones and playground zones. Okay? It's very, very dangerous because of the exponential relationship between speed and stopping distance. Okay? If you go twice as fast, you will travel 4 times further before stopping. Okay? It's simple physics, and there is nothing you can do to change that. Okay? Now, here's the part that people don't think about. Okay? Obviously, nobody in their right mind is going through a playground zone at 60. Please make it true. Please make that true. Okay? That nobody would go through a playground zone at 60. Okay? But do we talk ourselves into things like, that's only 10 kilometers an hour. If I go 40, it's not a big deal. Do we tell ourselves that? Okay? It's easier to talk ourselves into, it's not that much. It's only 10 kilometers an hour. Okay? Well, let's have a look at that instead. Let's say I'm going 40 kilometers per hour. Okay? 40 kilometers per hour is 11.1 meters per second. Okay? So if I do that calculation now with 11.1 in here, so initially it was 7.5. I'm only going 10 kilometers an hour faster, but I travel almost twice as far. Okay? Like, that's a big difference between 13 and 13.4 and 7.5. Okay? That's a long way. Okay? It's a lot further to travel if there's a little kid running out in the street. Okay? Now, here's the worst part of that. We tell ourselves it's okay to go 10 over. Okay? The average playground zone is about 250 meters long. Okay? So, if you go the speed limit, it'll take you 30 seconds. If you go 40, you know, the 10 over that you can justify in your mind. You save 7.5 seconds, which means you'll end up at the same red light as the person behind you going 30. Okay? 7.5 seconds is all that 10 kilometers an hour saves you. Now here's the really hard part to hear. If you make that decision and you hit a kid, you're saying that 7.5 seconds was more important than that kid's life. We don't think about those kinds of decisions, okay? But physics is immutable. That will happen. You will travel further. You will travel almost twice as far to gain 7.5 seconds and end up at the same red light as the person who went 30. Food for thought. You're all new drivers. It's food for thought. Okay. All right, so that is a fairly basic work energy theorem problem. Here's the good news. Work energy theorem problem.
Oh, just gonna ask use washer.
Yes, but put your phone in the pocket. Okay? All work energy theorem problems work basically the same way that one did. Okay? And that is this. That we start out saying work is a change in energy. Right? And our only challenge here is to decide, is it potential energy or is it kinetic energy? That's all we have to decide. Okay? Obviously, with somebody slamming on the brakes, they're reducing their speed, so that would be a change in kinetic energy. There's no mention of them going up a hill or down a hill and changing their height. Okay? If a question said, how much work would be required to lift something, okay, from the floor to a desk, then we'd be talking about potential energy. Okay? So we would just say, in the first situation, work's a change in kinetic energy. Okay? In the situation of lifting the box, work's a change in potential energy. and then it's just this. Okay, and in this one, that's all we're doing. And most of the time, one or the other, either initial or final, will be 0, which means that they're gone. And it ends up being just like the one we did. Force times distance equaled 1/2 mv squared. All I had to do was divide off the things I didn't want. Okay? Everybody with me there? Okay? We're gonna spend, several days on this. Don't worry, if you don't get it today, don't worry. Okay? We're gonna spend a lot of time on this. But it's very patterned, right? Once you learn the pattern, you won't have any problem with these kinds of questions. All right, I'm going to give you guys about a 4 or 5 minute break within the classroom here, okay? And just decompress, chat a little bit. Okay, so write this one down, and then see if you can give it a try. At least write down your givens. Okay, write down what the question gives you, and give it a little bit of a try, and then we'll go through it together. This is a work energy theorem question, and it is very, very similar, okay, to the slam on the brakes and avoid the child in the street question. All right, so prime example of a work energy theorem question. So we have a rubber band, and it's being stretched 0.85 meters. What did they give me there? What? Distance, yeah. Meters usually measures distance, right? Okay, so we can write down as our first given that we have the distance 0.85 meters. Okay, by a force of 60 newtons. So they gave me force. Okay? Force is always in newtons, by the way. Okay, so that is going to be 60 newtons. At what speed would it propel a 0.125 kilogram ball when released? Okay, so they gave me something in kilograms, right? So 0.125 kilograms, and they want to know speed. Would that be the initial speed or the final speed? So if you have a slingshot, that's essentially what this is, right? Okay, you put the ball in the slingshot, you draw it back. How fast is it going right now? 0. Its initial speed is while it's still in the rubber band. Okay, the velocity it would propel it at would be after the rubber band propels it. Okay, so we'd actually be looking for VF. And we would know from the context of the question that VI is 0. Okay, so sometimes you have to get clues from the context of the question. Obviously, height is never mentioned in this question. Would you agree? Okay, so what kind of energy about the ball is being changed? It's kinetic energy. Okay, that's the second step. Write down my givens, and from my givens decide, in this question, the work being done is changing the kinetic energy of the object. Okay? Now, from here, we start the pattern that works for all work energy theorem questions. Okay? What's the formula for work? What two things do I multiply together? Force and distance. Okay. All right, and to show change in kinetic energy, that would be the final kinetic energy, so 1/2 mvf squared, minus the initial kinetic energy, 1/2 mvi squared. Okay, if this was a potential energy question, I would have mghf minus mghi. The pattern still follows. Okay, since vi is 0, what's 1/2 times m times vi? 0. So can I just get rid of it? Right? Subtracting 0 doesn't really affect anything. Right? So I'm just going to get rid of that. Okay. Question wants to know what's V. How do I get V by itself? Divide. Right. Divide 1/2 of m over to the other side. All Now, that solves for VF squared. What do I want? Do I want VF squared, or do I just want normal VF? I want normal VF. So what do I have to do? Square root it, yeah. Okay. I followed the pattern. The pattern goes like this. You write down the gifts. You identify what kind of energy is being changed. You set force times distance equal to that change. So final minus initial. If any of them are zero, get rid of them. And then manipulate and solve. I know right now you're probably going, wait, what was step 2 again? Yeah, don't worry. We're gonna keep going over these. Once you'll have that pattern down in no time. Okay, and these will always work with a similar pattern. All right, so now I'm solving for VF. Now I just have to plug in my numbers. Okay, so the force was 60 newtons. Okay, the distance was 0.85. Okay, 1/2, and the mass was 0.125. So that's going to equal the speed at which we propel the ball out of the rubber band. Okay, so couple ways you can do this in your calculator. Okay, you can do it all in one step if you want to include all the brackets and everything. Totally up to you if you want to do it that way. Okay, but what I would do is I would just say, all right, what's the top? 60 times 0.85 equals. Okay, so that's the top. Now I'm going to divide that by the bottom. Okay, and then I'm going to square root that, because now I've done all of this, I just need to root it. Okay, so the ball is going to be propelled at 28.6 meters per second. Max, which one? Okay. Now, I could have also done it like this. Okay, I could have just gone, here's the root sign, bracket, bracket, 60 times 0.85, close. Okay, 0.5 times 0.125, bracket, bracket. I get exactly the same number, but I got to keep track of lots of brackets. Okay, if you're okay with that, you can do it in one step like I just did. Okay, but it's all the same steps, right? I did this, and I divided it by the bottom, which I did here, and then I square rooted it, which I did here. Okay, that's why I get exactly the same number. All right, so 28.6. Okay, so I would say, if you got that in your notes, which you should now, okay, is put above that work energy theorem, kinetic energy example. Right, because your kinetic energy, work energy theorem questions are all going to work like this. So it was a very similar pattern to the avoid the kid in the street question. All that was different in that question was we were looking for D instead of V. Okay? Still followed the same pattern. Okay. I'll do it. Okay. All right, let's have you try this one here. Okay. This one's actually a bit easier. You're just looking for how much work is being done here. Okay? You're not trying to find a force or a distance or a height. You're just looking for how much work is done. Okay. So in this one here, we got a mail carrier picks up a 10-kilogram package. So they gave me the mass. Okay? And it says they start on the 3rd floor of a building 30 meters above the ground. So that's where they started. I'm going to call that their initial height. And they go to the 10th floor. That's 100 meters above the ground. That would be their final height. Right? We're just looking for how much work is done. Okay? Now, what kind of energy is being changed here? Kinetic or potential? Potential. They don't mention any speeds here. We have to assume the person just walks up the stairs at a constant speed, okay? Because they don't say otherwise. So that means if we're talking about a change in height, we are talking about a change in the potential energy of this package, right? The work they're doing is giving it more height and thus more potential energy. All right, was I given force or distance here? Okay, and I don't need them. Question doesn't ask for them, and I can find the change in the potential energy. That's just going to be m times g times h final, my final potential energy, minus my initial potential energy. That gives me work. Okay, I don't need to multiply force times distance. There's more than one way to calculate work. Okay, so in this case, I don't even have to manipulate. I just have to plug in the numbers. I know the mass is 10 kilograms. I know G is 9.81, and the final height was 100 meters, minus 10 times 9.81 times 30 meters. Okay, that's the change in energy between the 3rd floor and the 10th floor. That is also then how much work the mail carrier does in carrying that package from the 3rd floor to the 10th floor. Okay, they do 6,867 joules worth of work because the potential energy of the box changes by 6,867 joules. Okay? Questions on that one? All right, don't worry guys, we're gonna spend days on this. You'll get the pattern down and it'll be like that for you, okay?